Chris Palmstrom Laboratory with Shojai and Mihir Pendarkar, and my research is indium arsenide, and in particular heterostructures, which are layers upon layers of different semiconductor materials, so you can get different electronic properties. And one major application is in hard drives, and in particular the heads of hard drives, the read-write heads, which do exactly what they sound. They read and write information. And the way how they do it is by exploiting this phenomenon called giant magnetoresistance. And the way how this works is that it changes the electrical resistance by the heads of magnetization. So in this case, it will allow electrons with only a certain spin to pass through it, or it will allow none of the electrons to go through it. So that way it reads or writes. And this itself is a heterostructure, what I was mentioning. And one of the proposed heterostructures is made of iron, silver iron with indium arsenide substrate, which is your foundation, the base. And you make this through the process called molecular beam epitaxy, in which you just get your substrate and just shoot hot atoms at it. So you start with an indium arsenide wafer, and then you shoot iron at it, and then silver, and then iron, and then you grow this heterostructure. And the reason why I use indium arsenide in this case is because it does exactly what I just mentioned right there. It does what you want. Unfortunately, during the fabrication process to make this particular structure, indium arsenide tends to break. It just fails, so you can't really use it. And so instead, what you do is that you start with gallium arsenide, and then you put on indium arsenide and the rest of the head. And gallium arsenide is much more robust, so it could survive the microfabrication process. Unfortunately, there's another problem. Growing indium arsenide and gallium arsenide is pretty rough, and I literally mean it's rough. You get roughness on the indium arsenide layer. So this part is the focus of this experiment. And in order to grow a better indium arsenide, gallium arsenide substrate, we have to understand where you get the roughness in the first place. And where you get that roughness is through defects, particularly dislocation defects. And dislocation defects are, as seen by this asterisk, it's just dangling atoms. And when you have and you'll see them visibly on the surface of your material as anisotropy pits. And the reason why you get them is because of a slight difference in the crystals of gallium arsenide and indium arsenide. So while they both share the same crystal structure, zinc blende, which is a lot like diamond, they have this length, what we call the lattice constant. It's different for indium arsenide and gallium arsenide. Because of this mismatch, this introduces straining when you grow indium arsenide on your gallium arsenide substrate. When there's too much straining, these dislocation defects appear on your surface, and you see this as roughness, and it will decrease the performance of your semiconductors. Since the straining depends on the thickness, we'll be growing various so the goals are we'll be growing various thicknesses. We will be characterizing the surface morphology using two different microscopy techniques, and we'll be measuring the transfer properties using the Hall effect experiment. Since I already mentioned about molecular beam epitaxy, and we'll be growing at these thicknesses, I'll jump right into the microscopy methods. So these two of them, we use atomic force microscopy, which it does exactly what this figure shows you, is that it just gets a microscopic tip, and it just taps your surface and keeps it at constant force. And it collects all the data, and since it's going up and down and doing throughout the entire surface, you can get a 3D plot of this, and this will be incredibly useful information. We also use optical microscopy using the Normarsky imaging. And Normarsky imaging gives you a nice 3D relief of your 2D image, and the way how it does that is that the optical link of the optical path link of your photon, as it enters through a transparent material, there will be a difference, and through this difference you can see otherwise subtle otherwise transparent defects that you won't see elsewhere. And to measure the performance of your semiconductor, we use the Hall effect with the setup called the Van der Waals setup. Now the Hall effect is a creation of voltage across your semiconductor under the external magnetic field. And typically it's only along your semiconductor, but the Hall effect introduces voltage across it. And when you have it arranged with the Van der Waals setup, you could calculate the sheet resistance, and in conjunction with the Hall coefficient from the typical Hall effect experiment, you could reveal a lot about your semiconductor. You could reveal any properties. And the two I'm going to be talking about is the electron mobility, which tells you how fast are the electrons moving through your semiconductor, and the electron density, which tells you how many electrons are being conducted through your material. So here are some data we collected. So notice the first three images. These are the images we typically expect. The 500 nanometer one's a little bit dirty, but that's fine. The 100 nanometer one, it unfortunately had some growth issues. Either the temperature was not correct, or there wasn't enough arsenic for the conditions to grow. And so you see these mounds, and so it just tells this data set is going to be off. But you can see with these mounds, you can also see them in the next series of the AFM. You can see that at least what we're seeing is real and not artifact. And that will tell us that the rest is also real. That the rest is real. So we do see these textures on them, and these textures it correlates to roughness. And the more interesting one, at least in my opinion, is the 3D images. And you can see it on the 50 nanometer one. You can see that there's a lot of these pits. These are the dislocations that I mentioned, and you can see that the number of these pits, they get less and less as your thickness grows thicker and thicker. So we can see it. So we can see a correlation between the roughness and the thickness, and we can also get a little bit of a further view of this roughness by doing some roughness analysis. So these figures are how you would see how we see the surface if you're only a nanometer tall, and this gives you an excellent qualitative measurement of how rough your surface is. But also it also tells you. But we can also get a quantitative number as well, so we can get some numbers by doing a calculation on it, and we can see the roughness ranges from 6 nanometers to 4 nanometers. And as for the performance, we saw some great results. We saw that the electron mobility went up as thickness goes up, but it doesn't make too much sense to just constantly grow indium arsenide on it, because that number eventually plateaus. And we did see the electron density go up as well. The anomalous 100 nanometer side, we also saw that correlation as well. So from this data, we could conclude, we could at least begin to say that for thickness, that thickness has the following effects on indium arsenide grown on gallium arsenide. It causes the thickness, as thickness increases, roughness goes down. electron mobility goes up, and so does the electron density. Now, in comparison with something much more ideal, such as indium arsenide boron, indium arsenide, which shouldn't have and doesn't have any, right, or at least it shouldn't have any defects because there's no lattice mismatch. It doesn't quite approach it to, well, unfortunately, the roughness is about it's 4 times as smooth, and the electron mobility is much more higher. In fact, the 10,000 is just that's a lower end figure. It could be up to 30,000. And so other things we could try to do is vary the concentrations, the growth, vary the use different buffer materials, such as including antimony, try different growth conditions, and we'll be doing that in the future so we could get better hardware and probably storing more data than you right now. Thank you.